Hi everyone, just going to start working through a set of solutions for this worksheet from today's lesson. I haven't worked through these for quite a while, so hopefully I don't to make too many mistakes as I go through. And I'm sorry I won't be in class today, but hopefully these solutions actually help you work through it on your own. Okay, so we're looking at exponential graphs and we're trying to go a little bit further than we have previously. We're going to talk about the domain and range, and we're also going to find the x-axis intercept as well as the y-axis intercept when it exists. So let's jump straight into it. Our first graph here, we've got f of x equals 2 times, don't forget the little time sign in there, 3 to the power of x. So we know that this is my base number here, my 3. That's my base number. So my base graph is 3 to the power of x. And it has been multiplied by 2, so therefore there's a dilation. That dilation factor of 2 will not change the x-axis or our horizontal asymptote. So there's still going to be an asymptote at y equals 0. The dilation does not change that asymptote. So we're going to put that in there. Our graph, this graph is a positive exponential graph. So if it is a positive exponential graph, we can see just by looking at it over here that it starts off really, really small and it's getting bigger and bigger really quickly. So it is a graph that is growing. Therefore, it is a growth graph, not decay. The domain of my graph, all of the possible x values, again, our graph's going to continue over forever this way to negative infinity, and although it's going up, it will also continue to the right to positive infinity. So my x values, or my domain, goes from negative infinity to infinity. Another way we could write that is we could just say it's all real values. The range, on the other hand, though, the range never drops below y equals 0. So my range is always the positive values. It's never down here. So the range is never negative. So I'm going to set up my range. I can do this 2 different ways again. I can start and go from 0, and there's an asymptote, so curly bracket, to infinity. Or I can actually do R with a little plus sign to say all positive real values. Okay, next one, y-intercept. This is the easy intercept to find. Y-intercept's when x equals 0. So when x equals 0, we're going to get f of 0 equals 2 times 3 to the power of 0. And we've learnt this in class already. We know that this part here would normally just have a y-intercept of 1. If I multiply that by 2, it's going to be a y-intercept at 2. So when x equals 0, y equals 2. Y-intercept, x equals 0, y equals 2. Let's mark that on my axes. And my graph's starting to come together. Now, do I have to bother finding an x-axis intercept? No, I don't. I know there's an asymptote there, so it's not going to exist. Not exist. That's pretty terrible English there. I probably should say doesn't exist. There we go. That's better. All right, next one. So we now have the graph of f of x equals 3 times a half x plus 4. Now, if we have a look over here, my base value is a half, but my graph for some reason is going the other direction to normal. The reason why that happens, if you don't remember from class, is this is actually 3 times 2 to the power of negative 1 to the power of x plus 4. And if we use our index laws, that's 3 times 2 to the power of negative x plus 4. And this negative up here, it creates a reflection in the y-axis. So we have a dilation by a factor of 3. We have a reflection in the y-axis, and we have a translation 4 units parallel to the y-axis, or 4 units up. Okay, so my asymptote This plus 4 is going to move the asymptote normally at y equals 0. It's not going to be there anymore. It's now going to be at positive 4. So we've got our grid lines here. My asymptote is at y equals 4. Y equals 4. My graph is starting as a big number and it's getting smaller and smaller and smaller. So this graph is not growing. This is absolutely an exponential decay graph. It's going down. My domain, like before, my x values will go on forever to negative infinity and forever to positive infinity. So my domain is all real values and my range is everything above. Okay. Y-intercept. Y-intercept is when x equals 0. So my usual process here, substituting x equals 0, 3 times half to the power of 0 plus 4. This becomes 3 times 1 plus 4, which equals 7. So when x equals 0, y equals 7. And I've got my y-axis intercept. Okay, cruising. Now my next graph, these ones here, we're just practicing, so don't freak out. Remember, I did mention that in the Year 11 course, we won't have translations left and right. This is absolutely a translation to the right. But we should be able to do this, and you need to know for Year 12 anyway, we should be able to do this because we've seen these translations in all of our other polynomials and quadratic graphs that we've already studied. So let's work through this. In this question, we're actually going to start by creating a table of values to give us a bit of a guide about what's going on with the graph, and that can help us answer the questions. So this is just a simple substitution activity. I always like to start with 0 because 0 is easier. So I'm going to have 4 to the power of 0 minus 1 plus 3, which is 4 to the power of minus 1 plus 3, which is 1 quarter plus 3. 3 is the same as 12 quarters, so it equals 13 quarters. 13 quarters. All right. Let's cut out that bit so I've got some space to keep working. Let's start again now. Let's work with x equals 1. If x equals 1, I'd have 4 to the power of 1 minus 1 minus 3. 4 to the power of 0 minus 3. 1 minus 3 equals minus 2. Minus 2. Okay, next one, when x equals 2. So it's 4 to the power of 2 minus 1 minus 3. 4 to the power of 1 minus 3, which is 4 minus 3, which equals not 3. Yes, it does. What am I talking about? Equals 3. Positive 3. Something seems strange there. I'm not sure that I've done that right from the beginning. I feel like I made a mistake earlier. I know what I did wrong. This one here should have actually been 1 quarter minus 3, which is 1 quarter minus 12 quarters, which equals negative 11 quarters. That looks better. All right, keep going with my table. When x equals 3, 4 to the power of 2 minus 3, which equals 16 minus 3, which equals 13. There's that exponential growth getting big quickly. Go back the other direction. I feel like there should be a pattern. I could possibly work it out, but I'm just going to substitute in values. 4 to the minus 2 minus 3, which is 1 over 16 minus 3, which is equal to 48 sixteenths. So 1 minus 48 sixteenths is minus 47 sixteenths. Tiny number. And then the last one will be 4 to the minus 3 minus 3, which is 1/64 minus 3. 3 times 64 is 192, so it's 192 64ths, which is minus 191 64ths. Hopefully I've done that correctly. What we can see though, without worrying too much about exactly what negative 191 on 64 is equal to, is these are going to be really small negative numbers. Okay, and if we think about our graph, what we already know, our graph has a base number of 4, so it's an exponential graph. It has been translated one place to the right, and it's been translated 3 places down. So I'm going to have an exponential graph that's translated 3 places down. So the asymptote will be at y equals negative 3. And we can see from my values in my table that my graph starts off as negative, and then it gets bigger and bigger and bigger and bigger and bigger up until the positives. It starts growing really quickly here. So I'm going to set up my graph, and I'm going to draw an initial graph that looks like that. I haven't taken any note at the moment of where this x and y axis intercept is. I'm going to fix this graph once I've worked them out. But I can work out my domain and range. I can say that it's going to be a growth graph. My domain is going to be all real values, and my range is going to be everything from negative 3 to infinity. My y-intercept is when x equals 0. We've already worked out what that is. It's minus 11 quarters, which was just a little bit less than minus 3. So that means this graph, sorry, a little bit greater than negative 3, is going to be down here, 11 quarters, right down here. So my graph has to go across and something like that. Oops, that's not a great graph, but we're going to work it out as we go along. So my y-intercept, 0, negative 11 quarters. Now we have to find the x-axis intercept. How do I find the x-axis intercept? The x-intercept is when y equals 0. So substitute that in. 0 equals 4 to the power of x minus 1 minus 3. Start rearranging our equation. We bring the 3 to the left-hand side. It becomes a plus. And now here we get to the place where we've been solving equations with logs. We cannot get the same bases. We've got a base of a 3 and a base of 4. That's not going to work for us. So we're going to use a logarithm. We're going to say log to the base 4 of 3 has to equal x minus 1. So we have the base, the number, and the power. The base, the number, the power. Okay, final step. We're going to do the opposite of minus 1, which is plus 1. So we take everything that we've already got and we plus 1 to get an answer for x. So we've got 4 to the power of something equals 3 plus 1. Now 4 to the power of something to equal 3, it's got to get smaller, so that power is going to be a small number plus 1. So my graph is actually going to go quite quickly. If you type this into the calculator, you can get a decimal answer, but I'm just going to approximate for now. I'm going to say 4 to the power of, if it was 4 to the power of 1, that's 4. So and 4 to the power of 0 is 1. So it has to be somewhere between 0 and 1. This has to be a fractional power. So it's a fractional number between 0 and 1, and then we add 1 to it. So if we've got a number between 0 and 1 and we add 1 to it, we're going to be somewhere between 0 and 2. So I'm going to put a dot there, join my two intercepts with an exponential graph, and let's get that to go away. So 0, negative 11 on 4, and then my other intercept will be log 4 of 3 plus 1, 0. And we just write it like that in technology free. And that would be my graph. Okay, one more to go. Let's see how quickly we can smash this one out. The first thing I'm going to do, I'm going to rewrite this expression as 2 times 2 to the power of negative x plus 3. So we have a dilation, a reflection, and a translation. My graph has to go up 3 places. If I move the graph up 3 places, there is going to be a y-axis intercept at y equals 3. I think I said y-axis intercept then instead of y-asymptote, but what I meant was y-asymptote. My graph, I initially think that it's going to be a growth graph. Okay, so I'm thinking, oh, it's an exponential graph, it's going to be growth. But when I rewrite it this way and I can spot that reflection across the y-axis and I draw a quick sketch like this, I know that my graph has to be a decay graph. It has to be getting smaller. So it's decay. And my domain, still R. Hopefully you're noticing the pattern there with our exponential graphs. They will always be R unless otherwise specified. My range has to go from 3 to infinity. My y-intercept, I'm going to substitute in x equals 0. So it's 2 times 2 to the power of 0 plus 3, which is 2 plus 3, which is 5. So I've got 1, 2, 3, 4, 5. I'm going to put my dot there. I'm going to use my grid lines because that's good practice. And am I going to have an x-axis intercept? No, I am not. So I'm not going to spend any time trying to work out that x-axis intercept. Okay, I could complete the table. You guys can do that on your own. This video has already gone long enough. I'm not going to spend time doing that. I am just going to finish saying no intercept for x-axis, and the y-intercept is at 0, 5. And I'll end the video there. Hopefully that's helped you complete this task.